Good morning, students. Today we are going to see about AC generator. So generator is a device that converts mechanical energy into electrical energy. Generator is based on the principle of electromagnetic induction. So electromagnetic induction already you know. When there is relative motion between the conductor and the magnetic field, it results in the change of magnetic flux linked with the conductor. In turn, an EMF is induced in the conductor. The magnitude of the EMF is given by Faraday's laws of electromagnetic induction, and the direction of the magnetic field or the direction of the induced current is given by Fleming's right hand rule. So once again I tell you, electromagnetic induction is nothing but when there is relative motion between the conductor and the magnetic field, it results in change in magnetic flux linked with the conductor. As a result of change in magnetic flux linked with the conductor, an EMF is induced in the conductor. The magnitude of the induced EMF is given by Faraday's laws of electromagnetic induction, and the direction of the induced EMF is given by Fleming's right hand rule. Now we are going to see what are the main parts of a AC generator. So the main parts of AC generator is stator, then rotor, then brushes, slip rings. So these are the main parts. Among these four, the stator and rotor are the very important part of a AC generator. So a commercial generator will have a stator and a rotor. So the name itself states stator is a stationary one, and rotor is the part that rotates inside the stator. So now we are going to see this construction of stator and rotor in detail. So regarding stator, it is having a frame. This is the frame of stator. So the function of the frame of the stator is that it holds the stator core and the armature windings in a proper position. So this is the frame of the stator. In this stator frame, there are large number of ventilation holes, so that a good ventilation is provided for the armature coil. So these are ventilation holes. So they provide good ventilation for the armature coil. Inside this frame, we are having core of the stator. So core of the stator is made up of steel or soft iron. This core will have large number of slots. So this is core of the armature core. So this armature core is made up of iron or steel. So this is armature core. So it is kept inside the frame of the stator. So it has large number of holes in it, where armature coils are mounted on it. So we will have armature coil mounted to this hole. So it is fixed to a rigid support. This is the construction of a stator. So stator is having four main parts. One is the frame. The function of the frame is to keep this core and the armature windings coil in a proper position. To this frame there are large number of ventilation holes in order to provide good ventilation for the armature coil. Inside this frame we are having core, armature core. This armature core is made up of soft iron or steel. It has large number of cavities. Using this cavity, armature coil is mounted. So this is the construction of a stator. Next we are going to see construction of rotor. So construction of rotor, we are having this stator is having armature coil. This rotor is having field coil. That is, using this rotor only, we are producing the magnetic field. So rotor is having an axis which is rotated with a constant speed using a rotating mechanism. To this axis we are having two slip rings. So these are two slip rings. These two slip rings are connected to the axis. So this is axis. These two are slip rings. Slip rings. These slip rings are connected to the axis. When axis rotate, the slip rings will also rotate along with the axis. So to this slip rings, to the axis of the rotor, we are having pole. So this is salient pole. This salient pole has field windings. So coil is bound over it, and one end of the coil is connected to slip ring S1 and the other coil is connected to slip ring S2. So one end of the coil is connected to S1 and another end is connected to S2. So when this coil rotates, when this axis rotates, slip ring will also rotate along with the axis, and the salient poles, they are called as salient pole. The word salient means projecting. So when current is allowed to pass through this coil, one will behave as the north pole and another will behave as the south pole. So these coils are excited by using DC source. So we are having two brushes. So this is brush C1 and this is brush C2. The C1 and C2 are connected to a DC source. So when current is allowed to pass through these brushes C1 and C2, the C1 and C2 is always in contact with the slip rings S1 and S2. So slip ring S1 and S2. So one is positive, another one is negative. So current will reach the slip ring S1 and S2 and it will flow through the coil. When current flows through the coil, one of this core becomes north pole and another one becomes south pole. This is salient pole. And another type of rotor is cylindrical pole. This is cylindrical rotor. In cylindrical rotor, we are having a cylinder. So the cylinder is a solid cylinder and it has large number of cavities. Large number of cavities, and these cavities are cut on the surface of the cylinder, and this coil windings are wound over it. So we will have coils wound over it. So one becomes inwards and this will become outwards like this. Coil is wounded, and this cylindrical will have large number of coils. So this is called cylindrical rotor. The salient pole is used in low voltage generators and the cylindrical pole is used in high voltage generators. So these are the main parts of a generator. So already you know brushes what we are using in the rotor, and cylinders also used in this rotor. So what is the advantage here? We have seen that field magnet is rotated inside a stationary stator. So commercially producing generators will have this type of construction. So armature coil is a stator coil and field magnet is a rotor. So the advantage of having this is we can take the output directly from the armature coil connected to the stator. So there is no need for using slip rings to take the produced EMF from the coil. Secondly, selecting stator as armature coil, we can wind the armature coil firmly to the stator, and insulating this coil is very simple. So there is no problem in providing insulation for the armature coil. Not only that, by using armature coil as the stator, it minimizes the number of slip rings that we use. So slip rings are only used for the DC component in order to excite the rotor. So by selecting armature coil as the stator, it minimizes the number of slip rings that we use. So these are the advantage of selecting armature coil as the stator and the field magnet as rotor. So next we are going to see how this generator is working. So depending upon the type of generator, so generators are of many types. Depending upon the type of generator, from generator to generator, the number of poles and the type of pole that we use, the number of armature coil and the type of armature coil will differ. So in this section we are going to see a single phase generator and a three phase generator. So when a generator is said to be a single phase generator, that is what we are going to see now. So in single phase generator, the stator will have two conductors, conducting coils. So stator will have only two conducting coils. So this is stator. Two conducting coils, and the coils are connected seriously, in series, so as to form a single circuit. So when this rotor is rotated inside the stator, it will produce an EMF, a single phase EMF. So we are going to explain a single phase AC generator with a simple diagram. So as I explained already, in single phase generator, the stator will have only two conductors. So these two conductors are connected in series so as to form a single turn coil. So I am representing the two conductors. The stator that has as PQ and RS. PQ and RS are the two conductors, that is the two windings that is found in the stator. So these windings are connected in series to form a single turn coil. PQ, RS. PQ is one conductor, RS is another conductor. This conductor is found in the stator and this conductor is connected in series so as to form a single turn coil of single turn. Now, here we are having salient pole armature. Salient pole armature. Let this armature, initially this is north pole and this is south pole. So the magnetic field is acting in this direction. Magnetic field is acting perpendicular to the plane of the coil. So now the plane of the coil and the magnetic field are perpendicular to each other. So as per electromagnetic induction, when they are perpendicular to each other, so I am having a single turn coil and the magnetic field is perpendicular to the coil. So I am expressing the induced EMF graphically. So time angle is taken along the x-axis, induced EMF is taken along the y-axis. So initially 0. When the plane of the coil and the magnetic field are perpendicular to each other, the induced EMF in the coil is 0. Now, this salient pole is rotated in the clockwise direction. So when it is rotated in the clockwise direction, so we are rotating in the clockwise direction. This is the direction in which this field magnet is rotated. When this field magnet is rotated through 90 degree, pi by 2, then what will happen? This coil and the magnetic field becomes perpendicular to each other. When they become perpendicular to each other, at that time the induced EMF becomes maximum. Again, when the coil is rotated through 90 degree, totally it is rotated through 180 degree. At that time the induced EMF becomes 0. So when it is 90 degree, the current will flow from PQ to Q and from R to S. This is the direction of the flow of current. When it is again rotated through 90 degree, the EMF becomes 0. Again when it is rotated through 90 degree, totally it is rotated through 270 degree. At that time, the induced EMF changes its direction. So now it moves from S or QP. Again, when it is rotated through 90 degree, again the EMF becomes 0. So when we graphically draw the induced EMF in the stator or armature coil, the induced EMF varies in the same way as that of a sine wave. So the EMF produced in a single phase generator is shown graphically like this. For detailed diagram, you can refer to the book. Secondly, we are going to see a three-phase AC generator. In three-phase AC generator, we are having stator of this type. So this is the frame of the stator. Inside the frame, we are having the core. This core will have 6 slots. 6 slots were cut. 1, 2, 3, 4, 5, 6 slots were cut. 1, 2, 3, 4, 5, 6. This 1 and 4 were connected to form one coil. This 3 and 6 were connected to form another coil. These 2 and 5 were connected to form another coil. So, each coil differ from each other by an angle of 120 degree. 120 degree. So, one of this coil 1, this is coil 2, and this is coil 3. So, this is the construction of stator. So, it will have 3 separate coils. Now, when the armature coil has 3, they will produce, and the rotor is rotated inside this armature, it will produce EMF. The induced EMF can be graphically represented like this: 0, 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330 and 360. When the first coil is perpendicular to the magnetic field, the induced EMF in the coil is 0. So that as the coil is rotated, it will produce EMF like this. When the coil is at 120 degree, at that time only the second coil will produce an EMF. Like this. The third coil will produce when the first coil is rotated through 240 degree. So the induced EMF in the 3 coil will differ like this. So this is how a 3-phase generator is working, and each coil will produce an EMF. E1 is the EMF of the produced in the first coil, E2 is the EMF produced in the second coil, and E3 is the EMF produced in the third coil. Each EMF differs from each other by 120 degree. Such a generator that produces 3 EMF and each EMF differ from each other by 120 degree is called as 3-phase AC generator. So this is how we are having a 3-phase generator. Suppose if the armature coil is having 2 coils and each differ from each other by 90 degree. kVA, then it is called as two-phase generator. So commercially we are having single-phase generator and three-phase generator. The advantage of three-phase generator is that for a given power, a high amount of power can be drawn or we can get by using three-phase generator. For a given capacity, the size of the generator is compact for three-phase generator. Not only that, transmission is very cheaper in the case of three-phase generator. So this is the advantage of having three-phase AC current. Three-phase AC current. Next we are going to see transformer. So transformer is a device which is used to transfer electric power from one circuit to another circuit. So we are going to see transformer. So transformer is a device which is used to transfer electric power from one circuit to another circuit. So this transformer plays a vital role in electric power transmission. So when you consider electric power, this electric power is produced in different modes. So we are having different modes of production of electric power. So electric power, namely hydroelectric power, thermal electric power, atomic power, windmill, or the different sources which is used to produce electric power. The power stations are located only in the remote area. So the electric power produced by these electric power stations has to be transmitted to the place where it is utilized, or cities or factories. It has to be transmitted. So while transmission of this electric power, this transformer plays a vital role. So in construction, a transformer is having three main parts. One is the core of the transformer. So core of the transformer is nothing but it is made up of large number of soft iron core. So soft iron is usually selected as the core of the transformer. To this core of the transformer, we are having primary coil. Primary coil. So this is primary coil and this is secondary coil. This is secondary coil. To this primary coil, input power is supplied and the output is taken across the secondary coil. This transformer works on the principle of mutual induction. Mutual induction. Usually in transformer, they used to select a high mutual induction coils where the mutual induction is very high. So since transformer is based on the principle of mutual induction, so what is mutual induction? It is the property of the pair of coil to produce induced EMF in one coil when the magnetic flux link with the other coil changes or when current through the other coil changes. So this is called as mutual induction. So transformer is based on the principle of mutual induction. So when a varying AC current is applied to the input of the primary coil, it produces change in the magnetic flux. This change in the magnetic flux that produced in the primary coil produces change in the magnetic flux in the secondary coil. Due to the change in the flux in the secondary coil, an EMF is induced. Suppose let Np be the number of turns in the primary coil and Ns be the number of turns in the secondary coil. if these two coils are mutually clubbed together, that is, all the flux linked with the primary coil is also linked with the secondary coil. Any change in the flux in the primary coil will have the same change in the secondary coil. So when magnetic flux linked with the primary coil changes and EMF is induced in the primary coil, let Vs be the applied input voltage. Since it is an AC voltage, it will vary with respect to time. This will produce change in the magnetic flux. Let Vp be the voltage produced or induced EMF in the primary coil. So the induced EMF in the primary coil is equal to minus Np into d pi b by dt, according to Faraday's laws of electromagnetic induction. And similarly, due to this change in the magnetic flux in the primary coil, this change in the magnetic flux also occurs in the secondary coil. So the induced EMF in the secondary coil is given by Vs is equal to minus Ns into d into by d by dt. So now Vs by Vp is equal to minus Ns into d pi v by dt divided by minus Np into d pi b by dt. So this will give Vs by Vp is equal to Ns by Np. So this ratio is called as transformer transmission ratio. This transmission ratio is given by K. For an ideal transformer, the input power is equal to output power. That is, input power is, if Ip is the current, input current, and Is is the output current. So for an ideal transformer, Vp into Ip is equal to Vs into Is, or Vs by Vp is equal to Ip by Is. But we know Vs by Vp is equal to Ns by Np. So we can write Vs by Vp is equal to Ns by Np is equal to Ip by Is is equal to K. So this is the transformer rule. For any transformer, this equation holds good. So here I told that input power is equal to output power. This is only for an ideal. So for an ideal transformer, we have seen that Vs by Vp is equal to Ns by Np is equal to Ip by Is is equal to K. So this equation holds good for any kind of transformer. But in actual practice, no transformer is ideal. No transformer is ideal. So if our input power is equal to output power, this is the transformer transmission ratio. So for an ideal transformer, this K is equal to 1. If it is ideal transformer, transmission ratio must be equal to 1. But in practice, no transformer is ideal. So depending upon the value of K, we can classify transformer into two types. When K is greater than 1. So K is greater than 1 means Ns by Np is greater than 1, or Ns is greater than Np, or Vs is greater than Vp, or Ip is less than Is. So Ip is greater than Is. This type of transformer is called step-up transformer. Step-up transformer. So what is step-up transformer? A step-up transformer will produce increased output voltage with decreased current. So it will increase the voltage but decrease the current. So in a step-up transformer, secondary voltage is greater than primary voltage. So it will produce an increased output voltage but decreased output current. So a step-up transformer will transform low voltage with high current into high voltage with low current. And similarly, for a transformer, if the transmission ratio is less than 1, we will have Ns is less than Np, Vs is less than Vp, and Ip is less than Is. So such a type of transformer is called step-down transformer. So what is called this step-down transformer? It is a transformer that transforms high voltage with less current into low voltage with high current. So thus we are having two types of transformer. So Ns is greater than Np. If the secondary winding is greater than primary winding, it is a step-up transformer. If the secondary winding is less than primary winding, it is a step-down transformer. Next we are going to see efficiency of a transformer. So the efficiency of a transformer is given by eta. So already I told you for an ideal transformer, input power is equal to output power. So efficiency is obtained by output power by input power. Input power. If output power and input power are equal, then eta should be equal to 1. But I already told you that no transformer is ideal. So a real transformer will have eta always less than 1. Always less than 1. So no transformer is having efficient equal to 100%. 100% efficiency is not possible in a transformer. So what is the reason for not having 100% efficiency in a transformer? There are some losses in the transformer. So what are the losses in transformer? First we have to see iron loss. So what is called iron loss? Here in a transformer we are having primary and secondary windings are on the core. The core is made up of soft iron. So as the current flowing through the primary coil is a AC current, the core of the transformer is magnetized and demagnetized for every cycle of AC current. Since the core of the transformer is magnetized and demagnetized and is taken through the cycle of magnetization, there occurs loss due to the hysteresis. This loss is called iron loss. So this is minimized by using core of the transformer which has low hysteresis loss. Usually silicon steel is selected. If silicon steel is selected as the core of the transformer, we will have less loss due to hysteresis. Second loss is the copper loss. So we know primary coil and secondary coils will have insulated copper wires. When current is allowed to pass through these copper wires, due to Joule's heating effect, some amount of electric power is wasted in the form of heat energy. This loss is called as copper loss. This copper loss is minimized by using thick wires of negligible resistance. Thick wires of negligible resistance. The third loss in transformer is the flux leakage. So when you consider transformer is having primary coil and secondary coil. In actual transformer, the flux linked with the primary coil is not fully linked with the secondary coil. So there occurs some leakage of flux. This is called as flux leakage. This flux leakage is minimized when one coil is wound over the other. So using shell type core, when one coil is wound over the other, then this will minimize the flux leakage. So these are the different losses in the transformer. Because of these different losses in the transformer, no transformer is said to have 100% efficiency. Next we are going to see electric power transmission. As I already told you, electric power is produced in different modes, different methods. So the electric power produced in the power stations has to be transmitted through long distance. So they have to send through transmission lines. So when electric power is sent through transmission lines, usually there occurs some loss due to Joule's heating effect. So Joule's, according to Joule's heating effect, heat produced when current is allowed to flow through a conductor is given by I square R T. So H is equal to I square R T. This amount of heat energy is wasted when current is allowed to pass through a conductor. Electric power wasted is given by H by T. H by T is equal to I square R. So this amount of electric power is wasted when electric power is sent through the transmission line. So I square R. There are two ways to minimize the electric power loss. One is to decrease the current. Second one is to decrease the resistance. When I decrease the resistance, I have to select transmission lines of huge cross-sectional area. Thick wires I have to use. When I use thick wires of copper or aluminium, the cost of the transmission lines becomes large. So usually what they used to do, they follow another method. They will decrease the current by increasing the voltage. Now we are going to see a simple example how the decrease in current reduces the power loss. Suppose I am having electric power of 2 megawatt. So this 2 megawatt electric power has to be sent through transmission lines whose resistance is 40 ohm. We are going to see two cases. In the first case, it is sent through transmission lines whose potential difference is 10 kilovolts. 10 kilovolts. Now I am going to calculate how much of electric power is wasted when this power is sent through this transmission line of resistance at this voltage. So in order to find out power loss, I have to find I square. So electric power is given by VI. Therefore, I is equal to P by V. So P is nothing but 2 megawatt. 2 into 10 power 6. Voltage is 10 kilovolt. 10 into 10 power 3. So this will give 200 ampere. So when I send this electric power, 2 megawatt of electric power through the transmission line of 40 ohm, current through the transmission line is 200 ampere. So let us calculate what is power loss. I square R. I square R is equal to 200 square into 40. Right? Therefore, power loss is equal to to 200 square into 40 divided by 2 into 10 power 6 into 100. So let us consider percentage of power loss. So this will give 4, 6, So this will give 4 into 10 power 4 into 40 by 2 into 10 power 6 into 100. So we will have 4 fours are 16. 4 fours are 16. 16 by 2. So percentage of power loss is equal to 4 fours are 16. 16 by 2 into 10. That is 8 into 10. So that is equal to 80% of the power is wasted. So if you consider 2 megawatt power, in this 2 megawatt power we are losing 80% and the remaining 20% only reaches at the other end. We are going to see the second case. So second case is we are sending the same amount of power 2 megawatt, same resistance 40 ohm, but the voltage is 100 kilovolts. So as per current through the transmission line is equal to P by V 2 into 10 power 6 by 100 into 10 power 3. So you will have 1, 2, 5. So we will have 20 ampere. So percentage of power loss. Power loss is equal to I square R by P into 100%. That is 20 square into 40 into 100 by 2 into 10 power 6. That will give 400 into 40 into 100 by 2 into 10 power 6. 1, 2, 3, 4, 5. Right? So you have 4 fours are 16 by 20. That is equal to 0.8%. So only 0.8% of power is wasted in the transmission line when we reduce the current. In the initial case, current is 200 ampere. Now the current is 20 ampere. So in electric power transmission, what we are doing, before power is transmitted, so we are having, this is the power station. So I will draw a diagram and explain the electric power transmission. So this is powerhouse. So when power is produced, before sending through the transmission line, it is stepped up using transformer, stepped up, and it is given to the transmission line. At the receiving end, again it is given to a transformer. So this is step up transformer, this is step down transformer, step down transformer. So again it is step down. So this is how transmission is carried out. So while before transmission, transmitting the electric power, it is stepped up using suitable transformer so that current is reduced very low and voltage is increased very high and sent through the transmission line. At the receiving end, again it is given to the step down transformer, and from the step down transformer it is given to the cities or the houses or the factories which use this transmission line. So for more clear, you can refer to the book. Thank you.